All right, well, hello, physics students. I am making another angle launch projectile video because the first one that I made, while it was a good problem, it was maybe a little outside the scope of this course. There were some steps in there that we haven't really done in this class, and it was just a pretty complex problem. So I just want to do a problem that's more familiar to us, just so we, again, can see the process and kind of understand, you know, this toolbox of equations, if you will, that we can use when we solve these problems. So this problem, we have a long jumper that's going to be leaving the ground with an initial velocity of 12 meters per second at an angle of 28 degrees. We need to determine the time of flight, the horizontal distance or the range, and the peak height of the long jumper. Okay, so the first step that I would like us to take when we solve these problems is to determine what those components of the initial velocity are. Okay, so we know that our initial velocity is 12 meters per second, but remember that's at some angle, and this angle is 28 degrees in this problem. So our first job should be to figure out what this v initial x is, and then what this v initial y is. Once we figure out those two things, we can pretty much kind of just forget about this v initial, okay, this 12 meters per second at the 28 degree angle. So as always, just recognize that this is a right triangle, so we can just very simply use our trig functions to figure out what those components, those velocity components are. So v initial x, we're going to be using the cosine function here. So we're going to say that v initial x is our v initial, which is our hypotenuse, times the cosine of 28 degrees. And if we plug and chug there, we're just plugging in 12 for v initial, we should get a value of 10.59 meters per second for v initial x. Now for v initial y, we're going to be using sine, okay, because our v initial is the opposite side from this angle. So we're going to have v initial times the sine of 28, and we're going to get a value here of, of 5.63 meters per second. Okay, so there are our components. Now we can draw our nifty XY chart to organize our information now. Okay, so we know that in the x direction, we know v initial x is 10.59 meters per second. And remember, horizontal velocity is constant, so whatever this v initial x is, that's going to be the velocity throughout the whole path of that long jumper. Now, what else do we know in the x? Not much. We ultimately need to find delta x, so we don't know that, and we also don't know time in the x. In the y direction, we know v initial y, which is our 5.63 meters per second. We know our acceleration in the y direction, which is just our acceleration due to gravity, and that's our negative 9.8 meters per second squared. And what else do we know in the y? Not a whole lot. We need to ultimately find what delta y max is. We need to find what that max height is. We need to know what time is. Okay, we don't know what time is. So yeah, we're kind of stuck here a little bit. But the first thing that we should always try and do in these problems is to figure out what that time in the air is. Now, remember with these angle launch problems, you know, what these look like, we have a path that looks like this. I don't know why I did it with dots. It's kind of hard to see. Okay, so we have a path that is parabolically shaped, and we know some vital information right at this point here at the peak, at that max height. We know that Vy is equal to 0. Okay, 0 meters per second. So that can be very valuable for us in terms of finding our time here. Okay, so essentially what we're going to be doing in this problem is we're just going to split it up in half, and we're going to say that at this point, this is going to be our v final in the y. So we're going to be working in the y direction to figure out what our time of flight is. Okay, so I'm going to be using this equation right here. And I don't want to use yellow. We'll say that v final in the y is equal to v initial in the y plus our acceleration due to gravity in the y times t. And we can just rearrange this to solve for t now. So t is going to equal v final y minus v initial y divided by our acceleration due to gravity, which is our acceleration in the y. Okay. Now, if we plug and chug this, recognize that for v final y, we're going to be plugging in 0 meters per second, because we're going to say that we're just going to cut this path in half. So v final in the y is going to be 0. Plugging in everything, we're going to get a time of 0.57 seconds. Now, just be aware, because we cut this path in half, this is only our time to get up to this point. So to find the total time that that thing is in the air, we just have to multiply this value by 2. So we should be getting then a time, and I'm going to erase my times here, we should be getting a time of 1.15 seconds. Okay, and I'm just going to fill that into my T chart. Okay, now the horizontal distance. This is pretty easy now. We have 2 knowns here in our x direction and only 1 unknown. And remember, in our x direction, we can just use our very simple velocity equation. So we can say velocity in the x is equal to delta x divided by t. Arrange that to solve for delta x. We're going to have vx times t. And if we plug and chug that, we're going to get a delta x of 12.17 meters. Okay, so that is our delta x. Boom. All right. And finally, C, or the peak height of the long jumper. Now, we know v initial in the y, we know acceleration in the y, and we know time. So we have 3 knowns and 1 unknown. So we can use, again, one of our kinematic equations. We can say that delta y max is equal to v initial times time, that's v initial in the y, times time, plus 1/2 acceleration in the y times t squared. And now we just have to plug in all of the stuff that we know here. Okay, I'm not going to do that because all we're doing is plugging this stuff into our calculator, and we should get a delta y max. Okay, this is the max height of that long jumper to be 1.62 meters. Okay, so just to summarize kind of this process that we take, the first step that I always want you to do with angle launch problems is figure out what those components are just using cosine and sine. Okay, and then the next big step that we need to do is we need to figure out what that total time is. And often it's easiest for us, if we know this initial velocity in the y, to just cut that path in half and say that v final y is at the peak here, and we know that that's 0. So we can just use this simple kinematic equation right here. Horizontally, remember that the most complicated equation we use is just this velocity equation, because there is no acceleration in the horizontal direction. Now, before I end this video lecture, I want to just give you a little toolbox. Uh-oh, why didn't that move? Okay, there we go. I just want to give you a little toolbox of equations that we can use in horizontally launched projectiles, or non-horizontally launched, angle-launched projectiles. So in the x, the only equation that we're ever going to use is this Vx is equal to delta x divided by t. Okay. In the y, we can get a little more creative. Often we'll use this guy right here, and this is often used to find the time that thing is in the air. And then we'll also use this. delta y is equal to v initial time plus 1/2 at squared. These are kind of the big three equations that we can use in these problems, and they just need to be manipulated, and you need to know when it's right to use them. But remember, if we know three things and we don't know one thing, we can use any of those kinematic equations. Okay, so with that being said, I hope that this video was helpful, and take care, physics students.